The flow.
I will be reviewing these several papers starting from papers from 2018 and up until now, um, and the main goal is actually this combining of approaches, of taking this classical approach, dealing with the statistics, internal statistics of visual data. We explain what it means in just a few seconds, and combine them into this new world of deep learning. So so let's first review this classical property. So as some of you may be aware, in visual data and especially in images, uh, small pieces of information like patches with size 5 by 5 or 7 by 7 tend to recur inside the image many times. So if you look at this patch over here, this is very likely to find a very similar patch also inside the image. And it's very important for me to make it clear that this is a very contrived example, and it looks like I'm showing the most convenient thing to show about this property. But this is only a toy example. So the patches I'm referring to are much smaller. They're much smaller than these green squares that you see now. This is just to exemplify. And this property is a very strong property. So it was empirically tested about almost 10 years ago, actually 11 years ago, on large data sets, and there is an overwhelming statistics about the recurrence of patches inside a single image. The reason for it is somewhat philosophical. I won't get into it now. If later on, someone want to discuss this during the question, then I can try to wave my hands a little bit. But this is a very strong property, and this was actually used many times for many works, starting with the image completion and in painting and texture synthesis, and then many denoising approaches like the very famous non-local means or BM3D, later on KSVD. And also in our lab, much before I arrived to this lab, I'm in Michal Irani's lab, the Weizmann Institute. They've been using this for stuff like visual summaries and for super resolution and other stuff. And this is using the fact that these patches recur within the same scale of the image. But there is another, a bit less known but also used many times property, which is the recurrence of patches across different scales of the image. So if I take this image and I downscale it several times, and we take a look at this patch over here, and so we will be able to find a patch in a smaller scale of the image, which is very close to the original query patch. And this property is also as strong as the recurrence within the same scale. So it also has these overwhelming statistics, and this was used also many times, especially in our lab, but not only. And so it goes as far back as the 80s. Some of you may be aware of this really old classical work, which then uh, formed the company using it. It's called fractal compression from the 80s. And then there were like many works in our lab. I think the most famous one was the super resolution from 2009, but also many stuff for deblurring and dehazing and others. And so the main idea in this approaches is taking advantage of these internal statistics and using them to solve many either inverse problems or other types of problems. And the great thing about all these methods is that they're totally unsupervised. So unlike what we usually do today, they don't require any training data, no long pre-training. Nobody thought about using GPUs and run tons and tons of data. The only thing you need is the test input itself. This is what you actually using in order to learn what you want to learn and solve the problem. Now the problem began so some short while after 2012, where it was the fact that if you're not doing deep learning, then nobody cares about you, and then and and actually it came to be that all these tasks like super resolution, denoising, dehazing, whatever, they were all won by deep learning approaches, so that all these previous methods were usually outperformed by deep learning methods using tons of data and whatever. And it seemed for a while, it seemed like you don't have to do anything of this type, and that the internal statistics can't be used anymore because the best thing is just having external statistics. So you get tons of data, and you can just train on it. And so we were hoping back when I started my PhD. So we were hoping that we will be able to somehow mitigate this so that we can have the best of both worlds. So we can enjoy these internal statistics and that do produce many things that external statistics are unable to do. May show an interesting example later on. But we do want to use this great power of deep learning. So our main idea was to take deep learning and combine it with internal statistics, and this gave birth to what we refer to as deep internal learning. And the main idea is that we're going to train an image-specific convnet, and we're going to do this at test time and on the test image only. So this gives rise to, I guess, I think, for most of you, to two main questions. And the first question would be, what the hell does it mean to train a network on a single image? And the second question would be, how can you do this with a reasonable runtime? So usually training networks is a very long process. So I'll try to explain this approach, and by now I believe everyone here has intuition enough to understand how convolutional neural networks operate. And I'll just and the truth is that let's say about 2 years ago, this wasn't that obvious what I'm going to say now. And so I'm going to make sure that we all understand this really important observation about CNNs. And I'm referring to fully convolutional networks. So one of the key ideas to what we're going to do is that we're going to use all the time, almost all the time, we're going to use fully convolutional networks. So these are networks that only has convolutional layers and activation, but they certainly don't have either pooling or a fully connected layers like classification networks usually do. And so one important observation is that a fully convolutional network is actually learning from this bag of patches. So every patch that the receptive that makes the receptive field of the filter that is traveling across the image makes its own piece of datum which has its own output at the other end of the network. So they can be seen as totally disjoint, and the number of such patches, don't be confused that these are overlapping patches. So taking away some, boundary effects, you can say that the number of patches you get is the number of pixels you have in the image. And you think about like images, I don't know, something like uh, for easy calculation, think about images that are like 1000 but over 1000 pixels. So this means you have 1 million RGB units, and this is more or less the number of patches, of overlapping patches you get. So you can get hundreds of thousands of data instances just inside a single image. And whenever you feed this into a network, you can actually see it exactly as if you were training on this batch of patches. Okay, so it operates in parallel, but each batch has its own output and its own contribution to the gradient that is calculated in order to update these shared convolutional weights. So this is exactly the same thing if you had them just in this huge batch for each iteration. And so this gives an answer to the question of how can you train on a single image, and the answer is you have tons of data just inside a single image, and you have hundreds of thousands of these patches. I point out that being fully convolutional is a very important characteristic. So if you had this fully connected layers for some reason at the end of your network, then just like this in one layer, all this data become just single datum. Okay, so the key idea is to have it fully convolutional. And the first work in which we demonstrated this approach was for the task of image super resolution, and this was together with also with Nadav Cohen, which was back then at IAS Princeton, and today is an assistant professor at Tel Aviv University, and of course with Michal Irani, my supervisor. So let's say a few quick things about super resolution, and we'll get back later to say a few other things. So in the world of deep learning for super resolution, the usual thing that you would do is exactly what you probably assume. So you get this data set containing low resolution and high resolution images matching ones, pairs, and you feed the low resolution images to this network of whatever architecture, and you use the high resolution images as the label, and you train it for hours or days or whatever needed, and now you have this trained network, and you can use it on this never seen before input images to get the super resolution. However, there are several drawbacks when you use this approach, and I should mention that this got really great results in this particular presentation. I'm not showing. I usually do show like results from really great super resolution works, and it really made the results much better than what they used to be before using deep learning for this. But there are several really important drawbacks. So one of them would be is that you can only use some kind of standard downscaling. So what happens is that the low resolution images are actually produced from the high resolution images, uh, and and the way you downscale an image is an issue. I'm going to discuss this each issue more thoroughly later on, but it's an issue. So the downscaling an image is done by convolution with some kernel and then subsampling. I believe most of you know that if you don't do any low pass filtering, you're going to get aliasing, and and this kernel that you do the convolution with turns out to be super important for super resolution. And what happened throughout all these years is that this downscaling process was done with a kernel called the bicubic downscaling with the anti-aliasing. So this is the default. So back then, everybody used MATLAB, and the MATLAB default is exactly this, the bicubic downscaling with anti-aliasing, and this became sort of standard. So for every validation test set or training set, the low resolution was produced from the high resolution using this exact downscaling, and and it turns out to be super important for the super resolution. Uh, to the extent that when you don't downscale it correctly, uh, so if you have an image that is downscaled differently, so all these super fancy networks, state-of-the-art networks, they actually fail miserably to the extent where what they do is no different than simple image interpolation. And another thing is that they really can't handle artifacts. So if you have noise or JPEG compression artifacts or any other thing, so if you think about it, these networks trained on many images, so once they see high frequency, they love it. They just want to amplify it, because this is what they're looking for. So if you have noise, they actually make the situation much worse. And another thing is that they're only applicable to the data they were trained on, and these networks are usually trained on natural images. But what if you have some different type of data, like medical data or microscopy or astronomy, like a telescope driven data, or any other type that is not from this, natural image distribution? So the network wouldn't be fit for it. And once you train such a network, so it's only good for the specific scale that it was trained for. So you have this network trained for X4 super resolution, and this is what you can do. So we were looking for a different method that can actually overcome all these problems. So, for example, you can decide on the fly whatever scale you want to do, and it doesn't even have to be the same scale for the horizontal and the vertical dimensions, and it would be applicable to whatever data you get on the fly, and can handle artifacts, uh, and actually can handle any type of downscaling method, uh, once you can estimate what downscaling method was used.
Is it okay
So
to ask a question about this?
yeah,
Uh,
sure.
what's the intuition? Why is that specific downscaling method is so important?
So we're talking about inverse problems. And the nature of inverse problems is that there is one direction which is really easy to do, and the other direction is hard. It's not invertible. So you need to use some kind of prior in order to invert it. And the downscaling kernel actually changes the relation between the input and the output. So if you downscale the image differently, now the pairs are going to be different. And super resolution networks, they usually train uh, the, differently from, say, classification networks. They have to produce an image at the end, and uh, they are fully convolutional, regardless of these internal settings that I'm going to mention. And and they work on actually on these patches in the side of their receptive field, so they can see many patches and perform well. But a downscaling kernel is uniform from the entire for the entire image, so you get much less data to train on. So I'm just referring to what may be the next question is, why don't you just take this regular network and instead of using standard downscaling, so just take by random some kind of kernel at each iteration, just sample a new kernel and then train the network on that.
Exactly.
And this in fact doesn't work. And so I used to say that it can't work, and then many times people said you don't know that, you can't know that, and then at some point some guys from Seoul National University actually did this experiment and reported that it doesn't work, and they did find a really nice other report. It does work, uh, but you cannot do it. You cannot just simply naively train your network with sampling random kernel at each iteration.
Basically, it's that uniform sampling of the downscaling kernel that is screwing things up.
Sorry, can you
You
ask again?
said you said that the downscaling, because it's done in a uniform manner across the entire image, not taking into consideration probably different interactions between artifacts in the image, then that's what's screwing up later on the super resolution reconstruction.
What I mean is that specifically the downscale method is the same for the entire image. So if each image has its own different, was downscaled differently, so finding out uh, finding out for each image what downscaling method was
Yeah.
used is possible. But if you don't do this, if you just say I'm going to be invariant to the downscaling process just by doing something that we do a lot in the world of deep learning, just by sampling it by random for each iteration and try to teach my network and not to not be affected by this. So there are some really smart methods of how to do that, but doing this just in this scheme, naive scheme, this wouldn't work. And okay, so here's our approach to it. So what we're saying is, okay, so we're now going to do a new thing. And remember that our goal is to train a network on a single image, just on the test image, and doing it at test time. So now we're going to have this single test input image that we have. And now we're going to do the counterintuitive thing, and we're actually going to downscale it. So now we have the downscaled version of the image, and we're going to feed it to some network, and uh, and this network will train to produce what is hopefully the super resolution of the low resolution of the original input image that we have. And to make sure that it does, we're going to train it in this autoencoder-like fashion, so that our goal would be just reconstructing the original input image from the downscaled version of it. Okay, we're just using this very simple L1 loss for it. And we're going to train it for a while, but for a short while. It's something like 9 seconds on a V100 GPU. And this is a very simple network. It's just a fully convolutional, 8 layers. No tricks there. Just conv value, conv value, conv value 8 times, and the last time doesn't have a value. And then with and for training it for these few seconds, we have this trained network, and now we're going to do the next thing is we're taking it and applying this trained network to the original size input image that we have. And you have to keep in mind that another characteristic of fully convolutional network is that it is applicable to any size of image. You have these filters, running across the image. They don't care about the size of the image. So you technically you can do this. And we're going to apply it and this is how we will get our super resolution. And the reason it works is, I'm going back to the preliminaries we talked about before, is that a fully convolutional network trains on image patches. And this specific network was trained to solve super resolution for patches that are, sorry, uh, uh, to solve super resolution specifically for patches from this downscaled image we have there. And now you have to remember the other thing that we discussed before, and this is that natural image patches recur across different scales of the image. So the same distribution of patches that we have here, you can see my cursor, right? So
Yes, we see.
so the same distribution of patches we have here is roughly the distribution of patches we have here. So if this network knows how to solve super resolution for patches from this downscale image, so by the same distribution, it is also able to solve super resolution for patches in the original input image. And this turns out to work really well. This gets a really nice result. But you should be aware that internal overfitting is a thing. So internal overfitting would occur when you get really superb results for the training, for the reconstruction error. But then when you apply it here, you're not going to get catastrophe, whatever what you do, it really works well. But you might not get ideal results, and you can get better. So for this, we just use whatever people use when they want to avoid overfitting. I mean, the first choice would be using data augmentation. So in our case, it means that we were not really training just on this original image. We were training on random augmentations of it. So this includes rotations and scaling of this image. And now we get, you can say, a much larger data set to train on. And one thing that is important, really important to mention here, is this downscaling step, because I was really preaching before about how important the downscaling is, and the question arises is, so okay, so I'm also constrained to some downscaling process. So here's the thing. So being agnostic to the downscaling process means that the downscaling method is also an input to the network. So in order for this to work right, you have to use the correct downscaling kernel in this downscaling process. So how can we know what the correct downscaling kernel is? So there are a few options for that. So one thing is, if you go to these, they do this every year, these super resolution competitions, and there the data is always, this standard thing with using bicubic downscaling. So you wouldn't have a problem there. What we actually did in this work for the challenge we call blind super resolution, where you don't know the kernel itself, is using this work from 2013, and this is a work by Tomer Michaeli when he was a postdoc at our lab with Michal Rani. And they had this is a non-deep learning method for estimating the downscaling kernel for super resolution. And this is also based on internal learning, just not deep internal learning. So back in 2018, this is the method that we used. And so we can estimate the kernel of the image and then use this estimation of kernel as an input and use this to downscale. Okay, it's important, maybe I didn't mention it, and it's important to say that what you want to do, you have to downscale the image in the same way that you believe that some non-existent high-resolution image was downscaled so that you get this input image that you have now. And the third option, and this is what I'm going to show you a bit later on, and is our own way for estimating the kernel using what we refer to as KernelGAN. This is a NeurIPS 2019 work that we had. So we have our own methods to estimate the kernel, which are not a part of this super resolution approach. And I should mention that I see many papers citing our work. Our work is this is called zero-shot super resolution, and for short ZSSR. I've seen many papers citing this work, and they do these comparisons, and they have, and many times these are papers about blind super resolution, and in many cases I can see images that were fed into ZSSR in order to get super resolution with really crappy results. And the reason it happens when you read through the paper is that many authors of papers, they're not aware of the fact that you have to input ZSSR the correct kernel. And for some reason, they assume that ZSSR supposed to, by its own, estimate the kernel or just do super resolution that is agnostic to the kernel. And I don't do anything about it. I don't write to them or anything because I find it like a weird thing to write to someone. You know, this figure you have in your paper is not right or something like this. But you should be aware that ZSSR is not a blind super resolution method. It's a super resolution method that is adaptive to the downscaling process, but the downscaling process needs to be estimated separately. Okay.
Assaf, what your comment right now, I would love to also write it by itself and the references for this talk. Okay, so afterwards I'll ask you to write down that 2 sentences or paragraphs, so we'll have it. This could be a
Okay.
nice answer, generic one for everybody.
Okay. As long as it doesn't make me sound like a crybaby. You know?
You choose the wordings.
Yeah.
You choose
Okay.
it, I'll just post it. Or
Yeah.
you can post it.
Yeah. Sure. Okay.
Can I ask a question?
Yeah. Sure.
So once again, I just want to understand your formulation. So you say that, so what is given to you? Is it that you have, you start from high resolution image, and then you select downsample channel in a smart way that there is no anti-aliasing, and the task is then to estimate this filter back when you have downsampled image. Is it correct?
No, the task is not to estimate this filter. That, you know, estimating the filter is done separately. The task is super resolution. So for super resolution, I'll show the results right away. For super resolution, you get a low resolution image, and you want to get a higher resolution image. What may be confusing is that in our method, you first down, even though you want to upscale the image, right? You have this image, you want to upscale this image. So it might have been a bit confusing. We first do the counterintuitive thing, and we actually downscale it, even though we want to upscale it. So eventually, you see the bottom row here. This is what you want to get. You want to get super resolution. You want to be able to get a high resolution version of this input image over here.
Yeah, I understand. But my question is, what do you, so your downscale, when you make this eye image that is in the bottom row, this very downsampled image, do you use your estimation to understand what is the right filter and to make this downscale?
Yeah.
So in fact, what happens that, let's say, you have image in the current resolution. You want to get an image that is, let's say, in higher resolution. But to do that, you just want to use recurrences. So you just make a downscale of your input image, and then you want to use your image that you currently have as a ground truth. And my question is, what is, it means that in a way it's a kind of deconvolution problem. If you think about classic methods, your network should reconstruct your, in a way, it reconstructs with inverse filter of inverse convolution filter, that is also known that it is a ill-posed problem because there is zeros in the filter and so on. But do you assume, so far it depends what is your, in the training stage, what was the downscale filter that you used? So this downscale filter that you used, how it was selected? Is it something specific or it's like a standard MATLAB?
So, okay, so I understand your question now, and what you said is correct. So looking at the classical way, this is an ill-posed problem, and we use this linear filtering, which in fact has zeros in the filter. You know, we must lose information if we have a downscaled version of the image, and now you need some kind of prior to go back. And it's not like you're looking for the inverse filter. I would choose a different wording for it, because you're now using this network, which is non-linear, and it's composed of doing two things. One, to be in the space of possible inverses of this non-invertible downscaling operation, and second, it needs to comply with some priors that this is what the network actually learns. And regarding the question about, so how do you choose the downscaling that you use here? So this is exactly what I was referring to in this note that we had over here. So there are several approaches of how to estimate this kernel, but the bottom line is that you either know it and then you can just plug it in, or you have to somehow estimate it. And then there are several methods to do that. So we had one method when we submitted this paper back in 2018, and then later on we had our own better way to estimate the kernel. Okay.
There are a couple of questions here and on YouTube. So Tomer is asking, can you estimate the kernel without the original SR source?
Yeah, sure. When we estimate the kernel, both in this work by Tomer Michaeli and both in our work from NeurIPS 2018, in both cases, we certainly don't have the high resolution ground truth. If we did, we didn't have to estimate the kernel and we didn't have to do super resolution, right? So we only have the input image, and we estimate the way that it was downscaled from this unknown higher resolution image, whether it exists or not. Okay.
And also on the YouTube, two questions. One was application using internal statistics, how to define any constraints on the type of problems this applies to.
I'm not sure how to address this question, because we had, during these years there were many problems that had this internal statistics approach, but I certainly can't, say that other problems that we never thought of can also be solved in this way too. I mean, you can be very creative and solve many tasks. I think that there are like hundreds of papers related to this topic. So the only thing I can say, I mean, the rule of thumb is that if you have this one, if you know that in your data, each single datum includes some kind of a known recurrence. And images are really a canonical example for this because if you think about the world that you're seeing, the world is made from patches, and you can, theoretically have this panorama image of the entire world, and then all the images of the world will be just patches in this huge image. So it makes sense to believe that image patches belong to some kind of non-trivial distribution that has some priors that you can actually learn. Hope this philosophical hand waving makes sense to you.
And
Yeah.
and there's
So
another question.
yeah.
We had a backlog. In a similar paper, deep image prior, it didn't have a guarantee of convergence. How do you know you've trained the initial phase long enough?
So I can discuss deep image. I'm actually going to explain specifically, very shortly, deep image prior because it is very related to another work that I'm going to show. So I won't say anything about deep image prior at this point. I'll just answer the question: how do you know stop the training process? And the fact is that differently, I guess, from no, not that different, but we just train, so the whole setup of the problem is unsupervised. But if you zoom in to this process of training, like this first instance of the network here that we train, so as far as the network is concerned, this is a supervised problem. It has a label and it has an input. So we just do gradient descent until we get convergence, and then we stop. I think the guy asking about deep image prior was probably referring to their method for denoising, where they have to do this early stopping. And so this is a whole other thing that this is. Fortunately, we don't have this problem at all. We just do this till full convergence.
Cool, thank you.
Okay, so let's check out some results. And so this image here, this is Checkpoint Charlie in Berlin. It's just an old photo found on the internet, and we don't know anything about the downscaling process. And you can see that it's kind of noisy, and also it is JPEG compressed. And if we look at so EDSR Plus is externally trained, I would say almost state of the art. And there are several works that do like marginally better for the ideal downscaling case. But EDSR Plus is really great. It's from Korea National, not Korea, sorry, Seoul National University, Kyung-Mu Lee's lab there. And so, and this is what they're almost externally trained, state of the art, trained on thousands of images. And this is what it's able to do. And if you look at our results, that you can see this is much sharper, even though it was trained just a few seconds. It only has 8 layers. So EDSR Plus is based on ResNet 155. So it's a huge network. And if we zoom in even more, then you can see the details. So for example, you can see, the gap between these guys' legs over there, or the details. Okay, so I'm flickering between the images, so you must be getting this with some delay, but I hope we still get this flickery.
Oh, we see it well.
Okay, so so you can see that we get details that are much better. And this is due to the fact that we were able to use a better estimated downscaling process, and that we handle much better noise and JPEG artifacts. Here's an interesting example. So in this example, this is actually using ideal downscaling. So we're not actually using any of the advantages that ZSSR may have with regarding to other methods, in the sense that there is no noise, there is no JPEG compression artifact, and this is not, and the downscaling is the one that is, you know, the comfort zone for the externally trained networks. But I think you can guess why this is a very comfortable example for us. You see this recurrence of elements across different scaling. This eye chart, this is the way it's built. So even for this ideal case, so we're able to get much better results comparing to the external state of the art. For example, we were able to find out that this character over here is G and not O. And here's some more examples. So this is a synthetic example. We downscale it with some random kernel. This is how it looks like. And for those of you interested, this is how the ideal bicubic kernel looks like. And this is what EDSR Plus got. And we estimated the kernel. We didn't estimate it perfectly, but we did. But we were able to estimate it to some sense, and we were able to get much sharper results. We have many more results in our paper and in our project page. Oh, this came out twice. I'll go quickly because I see that I spent too much time on this work. Here's another example. You can see how we can see these bars in the windows over there. They do exist in the ground truth. And for noisy examples, so externally trained networks, they just amplify high frequencies, so they actually make it even noisier. And we were able to get a much cleaner super resolution result. And here's an example for severe JPEG compression. And again, externally trained super resolution only makes it worse, and we were able to clean it. And this is all I have to say. We have many like quantitative comparisons in our paper and in project page that you can check out. And the next thing that happened is that we were looking for other ways to use this deep internal learning for many other tasks. And this is so together with Yossi Gandelsman, who was in our lab and today is in Google Research. We had this thing called double deep, where deep stands for deep image prior, was mentioned here before. And the general approach was that many seemingly unrelated computer vision tasks can be put under a single umbrella that we refer to as image decomposition. So we want to decompose images to layers. So I'll explain this by some examples. So for example, look at this image over here. So I can decompose it. I hope I can decompose it so that it would be this segmentation mask multiplied by this zebra pattern and plus the anti-mask multiplied by the background. And by doing so, I'm now able to get image segmentation, because if I retrieve this, then this mask I have here is the segmentation mask that I may be interested in. And I can do like other nice things, like make the zebra have the image without the zebra or whatever. And if we look at this image, so I can say that this hazy image can be decomposed to a thing that in physics and in dehazing challenges is called the transmission map. And so multiplied by the haze-free, by the clean image, plus 1 minus this transmission map multiplied by a thing called the air light. And of course, if I'm able to do this, then I have the haze-free image, so I'm able to do dehazing. And if you have this situation of transmission and reflection, okay, so you take, let's say you take a photo through a glass window, and you want to be able to separate them. So you can say that you have this coefficient, this transparency coefficient, multiply by the transmission plus 1 minus this that multiplies the reflection. And our approach was very much inspired and based on this very famous deep image prior work that came out in 2018 by Ulyanov, by Dmitry Ulyanov and Viktor Lempitsky and Andrea Vedaldi. And I'll do like very like oversimplified explanation of what they have there. So say you have this image, so for the deep image prior, you're going to take this network, fully convolutional. You're going to feed it with this constant random noise Z, and you're going to train the network to do this really seemingly simple challenge of just please just reconstruct the exact same image that is the label. Don't do anything too smart other than do that. And of course, this is a very easy task for a neural network just to learn to produce these specific pixels. However, they were able to show that this reconstruction can do more than just reconstruct what you already have. So they show many things, but I'll just talk about one example that is interesting, and this is that if this image happens to be a noisy image, so what you can do, you can train it, but then you do this early stopping. So you don't let it train all the way. If you let it train all the way, then you surely be able to reconstruct the image with the noise. But you don't do that. You just stop at some point, and then you're able to get this image without the noise. You're able to get a clean image. So it seems that the noise is being reconstructed at a later phase than the image content itself. And this is the way we formalize the reason for why this thing happens. So the entropy of patches, this is a fully convolutional network, and the entropy of patches in the original image is much lower than the entropy in the noisy image. So you get much more recurrence of patches. And by definition, when you have a noisy image, then so this means that you have much less correlation internally in the image. So if you take two patches that seem to be similar in the original image and you check them in the noisy image, they're not that similar anymore. So this very strong prior of recurrence inside an image simply doesn't exist anymore when you have this noise inside, and we did several experiments showing that when you mix images, so when you mix image with noise, so the high frequencies, these higher entropy elements of the image, they take more time to learn, because think about the network training. So there is a relatively simple rule to generate the entire image, but the rule for generating the noise has to be like super overfitting. Okay, there is nothing that is similar to generating the noise in one location in the image and similar to a different location in the image, where there is some kind of a nice rule governing the entire image for the original patches. So this brings us to our method that is called double deep. So deep stands for deep image prior, and so we do this double deep. So let's say we get some kind of image with mixed layers of any type that we want to decompose. So we're going to take a couple of these deep image prior networks, and we're going to train them together to do this really simple task, saying that the summation of both results needs to be as close as possible to this mixed inputs that we have. And of course, again, this is a very easy task to learn how to reconstruct this specific image. But here is where the magic happens. So every such network, such deep image prior separately tends to learn a separate layer of the image. And the reason this happens is that instead of just waiting, so we figured out that the noise comes at a later phase, but instead of that, we said, okay, So each of these network would do the simplest thing that it can possibly do, learn the simplest rule for the image. So the most natural solution is for each image to learn its own layer, because inside each such layer of the image, there is a high recurrence of patches and lower entropy. So it's a much more unlikely solution. For example, if one network would learn the entire image and the other one would learn, nothing, like a zero image. So what happens is that the entropy is much higher for learning the combination, or any other way you can split it other than having a minimum entropy for each side of the double dip would be the non-natural solution. So it has a very heightened tendency to do this, and and to make sure that nothing diverges from this tendency, we use another trick, which is called the exclusion loss, which is a very simple loss, basically saying that we penalize the result for having correlation between the two results, the two sides of the double dip. Now, you should know that this doesn't have to be just simple summation. So we can use this mask, saying that we're going to multiply one layer by a mask and the other layer by the anti-mask. And this mask can be learned. And the thing is that the regularization over the learning of the mask is what determines the task that we're going to perform. So, for example, if I want to do image segmentation, I'm going to encourage this mask to be binary. That is to say, I penalize it, any pixel value in the mask, if it's close to being 1/2. So I want it to be either very close to 1 or close to 0. And by doing so, I'm able again to learn the image, but now I'm encouraging this mask to be binary, and I'm able to use the double dip for segmentation. And for dehazing, I encourage this mask to be smooth, so that not to have too many gradients. And so we can do really nice, cool things. So here are some segmentation results. This is not semantic segmentation, and we don't claim it to be like state-of-the-art segmentation, but it does some really non-trivial segmentation, and this is using no other data, no supervision, and not any existing segmentation map that any human has ever had to draw by himself. Okay, so the only thing we have is the image.
Assaf, can I ask a question? So
Yeah, sure.
if I understand correctly, your mask is just, it's not constrained by some architecture, it's just a number of parameters equal to dimensionality of the image, and you just adapt these parameters so that distribution is like
So,
a certain
so,
time.
so this is what we originally did, but the truth is that the mask is actually learned by a third deep image prior network.
Mhm.
Yeah, but it can also work without it. It just works a little bit better using this deep image. Having a prior over the mask to also help.
Mhm. But then the question is, if it worked without deep network, so is it possible, like to train, not to train, just not impose with deep architecture on images and still getting some results only based on the losses?
So
Did
you mean
I mean,
training the images as if the image pixels are the weights or the parameters? Is that what you mean?
yeah, exactly. So, for example, instead of
I think I understand the question. Uh, um, so the short answer is no, and the reason lies along. I mean, okay, so the existence of the prior, which is the deep image prior, is a very important thing. So if it wouldn't be there, if you didn't have this fully convolutional network generating these images, then you wouldn't have this really strong prior that actually imposes recurrence of patches. and you wouldn't have any tendency to have this low entropy. The tendency to have low entropy is one strong characteristic that is encapsulated in the fact that this image is the result of a deep image prior network. Other than that, optimization directly on the pixels is a dangerous thing to do. I assume some of you are aware of this world called adversarial examples. So if you try to, in many cases, if you try to optimize directly on the pixels, so you're going to get really strange phenomenon of pixels and maybe changing just a little bit, and the loss gets you to be whatever you want the loss, whatever low you want the loss to be. So it's a really non-trivial thing. It is possible and it's done. Some of you are aware of style transfer and stuff like that, where they used it, but optimizing directly on the pixel is not a trivial thing to do.
And the second question, if it is already a network, can you just do the same, solving the same problem in downscale version and still get good results on the high resolution? Because using deep, you don't need actually to use images in a high resolution.
It's a good question. I'm not sure. I never tried it. I'm sure that it wouldn't be perfect, but it may, it might make some sense. Yeah. It may work to some extent. Okay, so thanks. So here's some more results, or here's for dehazing. We actually got results that were really good. These were at the time. I'm not sure what happens in this frontier today, but at the time these were state-of-the-art results. So we were able to really clean nicely and also to output the transmission map. And this is cool because the transmission map can be used to actually estimate depth in images. So the transmission map is actually an exponent of the depth, and we're able to also have this separating transparency. So this is an image taken through a window, and you can see that that we were able to recover the transmission and reflection. And it's really nice to see that we were able to see this Buddha statue that is inside, from one side of the window, which almost can't be seen in this original input image here. And another malicious application would be watermark removal. So you can just treat the watermark as another layer of the image and then separate the image to the watermark and the original image. So we were able to clean these protected images. This is for research intentions only. And here's a demonstration of video segmentation. So we have this video variant of the double dip, and you can see it's really not a perfect segmentation, but with really just small adaptation to video and no supervision whatsoever and no other data other than this video, we're able to get some reasonable results for video segmentation. Great. So the next thing we were after, so everybody were doing GANs. Everybody were using generative adversarial networks, and we thought that we can really use this internal approach together with generative adversarial networks with the goal of capturing what we refer to as the DNA of a natural image. And this DNA we're talking about is the distribution of patches inside this image. So that GANs learn distributions. So we were after learning the distribution of patches. So this work is together with Shai Bagon from Weizmann and Philip Pisola, which today is an assistant professor at MIT, and of course with Michal Irani. And so As you all know, a regular GAN trains on this collection of images and is then able to generate new images from the same image distribution. On the contrary, so internal GAN, or we refer to it as INGAN, trains on just a single image. But by this time into the talk, you're all aware that a single image is a collection of hundreds of thousands of patches. So we actually have tons of data as long as we train this correctly. And so INGAN generates new images from the same patch distribution. So for example, if from this input image, we can generate this new image, which has the same distribution of patches. So you see that this is a larger image, but the elements inside the image are not larger. So you don't have larger windows, you just have more windows here and more bars in this barn here in the back, and another sort of little barn that was created here. And we can do this, for example, smaller versions of the image like this. And this is a visual summary. So this can be seen as some kind of a thumbnail saying, okay, I don't want the entire image, but I don't want it to be just to squeeze it. So instead of all the windows here, it's enough to show just 3 windows here and have these barns smaller with fewer bars over there. And you can do this with changing the aspect ratio, for example, and other stuff. And so you can use it for retargeting or any other task for single image generation. So this is how it works. So we have this input image, and we have a transformation that we want to apply to it. We want to change the image. So, and we feed them both into a generator, which hopefully creates the transformed retargeted image. And to make sure that it does, and there's several options, and to make sure that it does, we feed it into a discriminator. Now, this is a patch discriminator. It's fully convolutional, and it produces a map rather than just a scalar. Okay, so we only have one real example, but which is the original image, and it contains tons of patches, and we have many fake examples for every time the generator creates one. And this discriminator judges patches rather than a full image. Okay, and so the generator's job is to fool the discriminator to believe that the patches it sees actually belong to the original input image and not to a fake one, not to a new generated one. So this is what the generator tries to do. Now, apparently, internal mode collapse is a thing. So, for example, if we generated just this image containing only grass, the discriminator would be just fine with it. It wouldn't have any problem, because all the patches in this image actually belong to the original input image. So the discriminator doesn't care. It would say, yeah, go on, this is good. So to avoid overfitting, what we did is we used this cycle consistency, which means we took the generator again, and this time we apply it with the inverse transform to what we did before. And this is just another instance of the same generator. It's shared weights, the same generator. And now we train it with this very simple L1 loss to reconstruct the original input image. And you can see that the second instance of the generator actually does the same challenge that the original instance of the generator has, because both of them needs to just do this retargeting. So this one always gets the same input, but has different outputs according to the transformation. And the second one gets various inputs, but always has to output the same result, which is the same as the original image. And the final loss of this thing is the GAN loss, and plus the reconstruction loss for this cycle over here.
A
And so
question
let's,
about the structure.
yeah.
So that's an interesting way to solve this problem. Did you think of other ways to try to account for the structure, or what was the motivation, or where did the idea come from to use the second GAN?
So the idea for this is not a second GAN, this is just a second generator. It doesn't
Yeah,
train on
yeah. Sorry, it's second
that.
generation.
So the idea was, in a way, there all the time. I mean, so this is in collaboration with Philip Isola today from MIT, but at the time he's one of the authors of CycleGAN. So it was a natural thing to do. And then finally, Shai, also collaborated in this paper of Shai Bagon, he came up with the idea to use just instead of this decoder back, said, why can't we just use the same generator again? And so we were joking that this is not an encoder-decoder network, this is an encoder-encoder network. And so this is how things turned out.
Nice.
So I'll try to demonstrate some results and explain what we're actually seeing. So if we stretch this image using INGAN, so you can see that we're not just, this is not stretching per se. I mean, this, you know that the corn seeds are the same size, we just have more of them. Okay, so this is a different way of enlarging an image. It's not like interpolation. And we can do this also in the other dimension. And you can see, oops, and we can see now that we have new corn cobs that were created. And interestingly, no two corn cobs are alike. So it doesn't just make this, repetition of the existing corn cobs. So what happens is that implicitly it has this distribution of corn cobs, which generates corn cobs, and it's constructed of this implicit distribution of corn seeds. You can see some are white, some are yellow, some have different shapes. They all have to somehow fit in this overlapping regime, but it's not like just repeating the same patches again. And since neural network is continuous, and we're able to train INGAN once and then apply it to any transformation at test time, we were able to produce these really nice videos that smoothly add or remove these elements. And here's another example. So you can see in this example, you can see how more fruits are added, but not just, it's not just fruit, because when needed, so new boxes, new crates with fruit are added or removed. So this is like a different type of resizing. You can refer to it as retargeting. And here you can see that the transformation doesn't have to be just resizing. So you can see affine transformations or just a general homography. And however we distort the general structure, inside the elements maintain their original shape and size. And in this example, this is Piazza Venezia in Rome. You can see how more poles are added, and you can see that no, the penguins are not getting any fatter, just new penguins are being born when needed. These are actually, I think, the forgot the name of how do you call the North Korean leader? Slipped my mind.
Kim Jong-un.
Kim Jong-un. So these are actually this is his army of female bodyguards, and you can see how new there is like an implicit face distribution here, and you can see the terraces here from Sapa, Vietnam. In some cases, this can make this illustration of biosynthesis. So this is New York, as you may imagine, and this is not a high quality, but you can see that you can do this transformation, and because patches are maintain their original shape, So it kind of looked like a view synthesis, like you take the image from different direction. But of course, nobody is perfect. So we have these failure cases. And the reason is that we have nothing semantic. We have no labels. We have nothing and no way that INGAN can know that humans don't have two heads. So the simplest solution when stretching this image is having this guy with the two heads. And in a way, this creates this bridging some gap between textures and natural images. So this, from single texture to multi-texture to rich to texture-rich paintings, and throughout really natural images, you can see this is very big objects in the image, and this just adds another peacock uh, when needed. And this is to show that the patch distribution captures this DNA of the image. So the point where we got now is that I actually reviewed 3 out of the 4 papers I was meaning to talk about. And the question arises, do we want to like try to quickly talk about the 4th paper, or shall we just like conclude here?
I
Peter.
would say let's cover the 4th one. Still, there's many people in the audience, and there will be the recording, so people can always look again.
Okay, so I'm sorry if I'm taking more of the time, more time of what you were hoping to spend. It's not going to be too long. So you may remember that in the ZSSR work that I presented, the first one, uh, I mentioned this challenge that is needed to estimate the downscaling kernel for the super resolution. So this work is together with Sefti Bell-Kliegler, and it was in our lab today in a startup called Desi here in Israel, and Desi AI, and and we were hoping to combine the approaches that we are now aware of. So we know about internal GANs, and we know about internal learning and super resolution, and we are asking ourselves, can we use an internal GAN to estimate the kernel for super resolution?
So,
And yeah.
Assaf, there was a question a half hour ago, but we were waiting with it. It might be the right time to ask it about this area, let's say. So Tomer asked, much of the work is estimating the kernel. That was the first question. And the second one was, which is the first network that uses GAN? Maybe you will explain during this part of the lecture.
I'm not sure I fully understand the question. Which was the first network to use GAN? What does it mean?
So that one I wasn't sure also. The first one, it was asking when you were showing the first part of the lecture that basically the question was about that, which was basically most of the work is to try to figure out what is the image reduction kernel, the image,
The downscaling.
yeah, the
So
downscaling kernel.
this is a super important part of the work, but there are two, even if you fully know what the kernel is, as in most super resolution works and that you see in most conferences and as in most super resolution competitions, usually the kernel is known, and it's still very challenging to do super resolution. But if you don't know the kernel, as we see in a minute, then the problem turns out to be much harder. And we talked about, and I'll remind you again that in super resolution we want to have a higher resolution version of the original image that we have, and we should know that each pixel in the original image is the result of convolution with some kernel and subsampling. And this is the way downscaling occurs even in optical devices. And this kernel can be, there's some examples that can feel what this kernel can be. And it has to do a lot with the optics that we're using, and also our hand movement. If we do this, move our hand from side to side, then we're going to have this very particular shape of the kernel. And it's hard enough to do super resolution when you know the kernel, but if you don't know the downscale method, then you have no chance almost to do super resolution. We've seen some examples to that before. This is very important for super resolution, and we're after this challenge called blind super resolution. And blind super resolution specifically refers to the challenge of super resolution where you don't know the downscaling kernel. And what we do know about the correct kernel, and this is we know from Tomer Michaeli's work at 2013, is that for various reasons, which I won't get into now, you can say that the correct kernel is the one that maximizes the patch similarity across scales. So we know that there's supposed to be a recurrence of patches across different scales of the image. And looking at this in another way is saying that if that the correct kernel, if you downscale correctly, then this characteristic occurs. So you can look for the kernel by saying what kind of downscaling would maximize the recurrence of patches across different scales of the images. And back at 2013, they were using this nearest neighbor approach. So they downscale the image, and then they want to find the patches of the downscale image. They want them to be as close as possible to their nearest neighbors in the original image, and then they can do this again and again. So they use this expectation maximization approach with nearest neighbors. And here's our approach. We were looking into doing this using an internal GAN. By this time, we had our work called INGAN, and the known also SINGAN from Tamarot Shacham and Tom Michaeli and Tali Dekel, and we were using an internal GAN in order to estimate the downscaling kernel. So here's how it works. We feed it into a generator that does downscaling. Now, we remember what we want is that the downscale image will have patches that are as close as possible to patches in the original image. That is, we want a downscale image with this, as much as possible, the same patch distribution as the original image. So we're going to use again a discriminator, and again this is going to be a patch discriminator that produces a map. And for each patch this discriminator sees, it needs to decide whether this came from the original image or from the downscaled image. So the generator's job in this case is to downscale the image in such way that to fool the discriminator to believe that the patches of the downscaled image are actually patches from the original image. Now, remember that what we want to assume, what we want to estimate is a linear process. And there rises the question, okay, so what kind of generator do we want to use here? So if we will use, what usually people use, which is a neural network, a non-linear neural network, then there is nothing that, there is no requirement for this to be linear or to make sense and to actually be a downscaling process. This can do whatever it wants if it's non-linear. So for example, it can just take the same patch over and over again, and again, the discriminator would say, okay, this is fine. I'm good with this because all of these patches are actually good patches. They belong to the original input image. So this can't work. So what we can do is say, okay, this has to be this linear process. So let's do it this way. And in deep learning terms, this single convolution with the downscaling can be called just as a single strided conv layer. So we did this, and we said, okay, this has to work, right? We're going to use this very simple one-layer network generator. It only has to learn what one convolution, how to downscale it. And these are the results we got comparing to the ground truth kernels that we checked, and you can see these are really crappy results. And we were thinking, we were trying to figure out why we're getting these results, and it took us quite a while. And this is and this is the very interesting uh, reason hypothesis we have for it. So it, I assume most of you are aware for this aspect in deep learning theory that it works because you have no bad local minima, or almost statistically no bad local minima. So whenever you train a network, you're going to get to a different local minima, to a different local minimum point, but they're all almost equally as good. This is a very important paradigm which makes gradient descent work in neural networks. But in our case, we sort of broke the paradigm because we, in fact, know that since what we're looking for is not the result of the network, but the weights of the network. So we have this ground truth, which is not a result ground truth, it's ground truth for what the weights of the network should be, which is the correct kernel. And there is only one like this that exists. So it turns out that we break this paradigm and create this optimization surface where there is only one good solution. All other local minima are just not as good. They're not as good as this correct kernel. And since we're using now a non-convex loss, our loss is a discriminator, but we're trying to find something that is unique, then the chances to converge to this exact minimum point, they're almost they almost don't exist. So wherever you're going to start with from this random point you're going to start, you'll just find yourself in this local minimum, unable to get to this only one desired existing global minimum point. So we can't use this. And at this point, we're actually stuck for a very long time, for actually months. And we sort of killed this idea. We thought that it can't be done. We left it alone until I had this very occasional phone call. And this was with Nadav Cohen today at Tel Aviv University. And he collaborated with us in our first super resolution paper. And he was mentioning at the time, he was this IIS Princeton, he's a theory guy, and he was telling me, just describing that he's looking at these things called linear neural networks. And I won't lie to you, I thought this is the stupidest thing I've ever heard, a linear neural network, because if you have a network so what's a linear neural network? It's simply a network that has no activations. And I thought it was stupid. So I thought, okay, these theory guys, they always look at these things that don't make any sense. Anyway, so the reason why applicatively this doesn't have can't have any use is that, think about it. This is just a sequence of matrix multiplications. And if you just, this is an associative operation. So if you just multiply all these matrices together, you can say that this is exactly the same as just having one single matrix, just one single layer. So this is linear regression disguised as a neural network. And this whole thing is linear. And this is true. But the thing is that the optimization of this creature called linear network is totally different. So what we have here is just different matrix decompositions of this single matrix that we have right here. But every weight we have in this network here, every parameter here, is not a parameter in this matrix here. The parameter in this matrix here is some kind of a multiplication of these numbers that are the weights of this network. And so the whole process of optimization is totally different. So let's say I'm able to optimize this linear network. What I have to do when I'm done is multiply all these layers together to get this one single matrix that would eventually be the wanted kernel that I can just linearly use. But the great thing is that there are infinitely many such decompositions. So for one linear process, there are infinitely many decompositions. So for example, think about it, that wherever you want inside the network, if you multiply one layer by some matrix A and the other one by its inverse, you're still getting the exact same result when multiplying all the layers together. So having infinitely many, this breaks the problem that we had before. So now we don't have just one local minimum, just as we have here. We have infinitely many local minima, global minima, actually, infinitely many, that they all match after we multiply the whole thing together to the same minimum point that we have here. Okay, so now this creature can be optimized, and there are many other really cool things that happen in linear networks that don't happen in just linear regression in terms of the optimization process. It's really interesting, actually. And now these are the ground truth kernel. These are the results I showed you before, which were really crappy. And now we're able to really get good results for estimating the kernel. And now the next thing we did is plugging the kernels estimated with KernelGAN and use them inside GSSR that I showed you before. We also checked for other methods that can get the kernels and input. There's a method called SRMD. And also, as far as we know, this is the first practical use of deep linear networks. So theory guys have been looking at these things for years, but for practical use, this is the first thing we are aware of. So we compare ourselves not to these. It would be too easy to compare ourselves to state-of-the-art non-blind methods. They do not better than interpolation. So what I'm showing you is comparison of our results with respect to the winners of the blind super resolution challenge that they have every year at CVPR. And so specifically this is called PDN, and this was made for blind super resolution. So we have this image here, and it was downscaled with some unknown kernel, and this is the PDN results. And you can see that using our estimated kernel, using our estimated kernel. Okay, this is a GIF. Okay, now, okay. And using our estimated kernel, you can see that we get much better results. You can see these fibers of the sleeve and the details in this lady's eye. This is due to the fact that we were able to estimate a much better kernel, and then we just use GSSR for the super resolution. And okay, I guess, and okay, so I guess this is all I'm going to show you about this. So we had, super resolution, and we had GAN, and we did many challenges like dehazing and segmentation, all using just information we had inside a single image. And I'll just let you know that this can be also taken to the temporal domain. So this is a work that I'm not a part of, and this was from our lab, but I wasn't part of it. It was when I was in Google, so it was shown in ICCV, and this is for temporal super resolution. You can see that when you have this video, you have this, and if you want to have a slow motion of it, this is really problematic because you have these severe blurring, motion blur artifacts, and you also have, if you look well, these temporal aliasing effects, and you must know it when you look at helicopters or when you look at fans like this one, that it can be seen as if it rotates to the other direction, and this happens due to the fact that the refresh rate of our eye is not fast enough, so it matches like swirling to the other direction. And I'm not going to explain all the work. I'll just show they did really nice work. So I'm sorry, this is the work by Liad Polak and Eyal Naor and George Pisha and Shai Bagon and Michal Rani. And you can see that many of these frame interpolation slow-mo, you have the NVIDIA super slow-mo, where many of them fail when you have this motion blurring. So they're able to use exactly the ZSSR approach with some other tricks on the temporal domain with space-time patches, and they were able to get a really nice slow motion with no aliasing and no artifacts, and even very famous like NVIDIA slow-mo and flawless, very famous methods tend to fail there. And for anyone, so I'm done here, and I'm sorry for taking too much of your time. I'll just say that we had at the last ICCV conference, we had actually a workshop about deep internal learning, and this is a great source for anyone interested in this topic, because there were many talks there. This was really cool. We had some really impressive, great speakers there, like Andrea Vidaldi and John Barron and Alyosha Efros, that were able to join us, and we also all of us organizers that you see here, we also gave talks about our works, and there were many short 5-minute oral presentations. So this field has actually really grown. There are today many works working in this field of deep internal learning. So if you Google this, you find the website, and you find the entire workshop was recorded, and you can see all these talks, and there are really some great works there. And that's it. I'm sorry for taking me so long. And if you have any questions, I'll be happy to take them now. So thank you all. I really appreciate it, you listening to me so far. And sorry again for being 17 minutes over time. Thanks.
There is a question in the YouTube live. Is there a recording of the workshop? So I'll probably ask you to send the link, and I'll add it to the references and stuff.
To the deep internal learning workshop.
Yeah.
Yeah, sure, no problem. So I guess if there are any questions left, then I'll take them, and if not, I'll set you free from this super long talk that you just had.
Assaf wrote a correct comment here. No need to apologize for the time. Thank you for giving us the extra time and telling and teaching us about this part also.
Thanks. I appreciate it. Thank you.
So I think there's no more questions. We can sum up. Assaf, if you have some words, and afterwards I will finish off.
No, I think I already concluded. Just thanks again to everyone. I really enjoyed giving the talk, and thanks Peter for inviting me, and great initiative. Well done.
Yeah, thank you, Assaf. The second time you're here, and each time it's good lectures and very thorough research and explanations. So thanks again for coming and giving us of your knowledge. To everybody who's still here, thank you for joining each time and participating and helping making this happen. You know, without the audience, without you being here, it wouldn't have existed. So thanks again. We've passed the 1,000 people on Reddit. We're past the 1,600 people on Meetup. So for me, it's always exciting to see things grow and become successful. I'm always looking for more interesting lecturers to come and teach. So let me know if you know of anybody who has interesting content and is interested in spreading it. We are on Discord and on Reddit. I'm always available there for any question you have, for anything. And not only me, the other people in the community are helpful there and pitching in. So feel free to share or ask whatever you have. We will be publishing the references probably today or tomorrow. So you will have it on the Discord immediately and on the Reddit also. I will say thank you again, everybody, for joining, and have a good day.
Thank you. Thanks.
Bye-bye.